The first hints that something was wrong arrived not as a single shocking image, but as a pattern emerging from the earliest deep-field observations made by the James Webb Space Telescope. Within months of beginning operations, JWST delivered infrared images revealing compact, bright galaxies at redshifts previously considered nearly unreachable. Some appeared at redshifts greater than 10, others approaching 13 and even 16, corresponding to times less than 300 million years after the Big Bang. According to long-established cosmological timelines, the universe at that stage should have been sparsely populated with small, irregular protogalaxies dominated by pristine hydrogen and helium. Instead, astronomers were staring at objects that looked far too evolved for such a young cosmos. But these galaxies aren't just distant dots, they're cosmic rebels, shining brighter and growing faster than physics should allow. Subscribe now and join us as we explore these impossible worlds that could rewrite everything we know about the early universe. The shock came from their brightness. These galaxies were not faint smudges barely rising above the background noise. Many displayed luminosities comparable to galaxies that formed billions of years later. JWST's near-infrared camera detected strong rest-frame ultraviolet emission, indicating large populations of hot, massive stars. In several cases, the inferred stellar masses exceeded 1 billion solar masses. Under standard models, assembling that much stellar material would require sustained star formation over periods longer than the universe had existed at that time. Redshift measurements placed these galaxies firmly in the early cosmic epoch. Their light had travelled for more than 13 billion years, stretched by cosmic expansion into the infrared range that JWST was specifically designed to observe. Follow-up spectroscopy confirmed the distances, ruling out the possibility that they were nearer galaxies masquerading as distant ones due to dust effects. These were genuinely ancient systems, shining at a time when galaxies were expected to be embryonic and fragile. The problem was not merely their existence, but their number. Early predictions suggested that only a handful of detectable galaxies should exist beyond redshift 10 within JWST's field of view. Instead, dozens were identified in relatively small survey areas. This implied a galaxy formation efficiency far higher than anticipated. The dark matter halos required to host such galaxies should have been exceedingly rare so soon after cosmic inflation. Yet the sky seemed crowded with them. To understand why this was so disruptive, it is necessary to examine the assumed timeline of early structure formation. After the Big Bang, the universe expanded and cooled, entering a period when neutral hydrogen dominated and light struggled to travel freely. During this era, matter slowly clumped under gravity. The first stars were expected to ignite around 100 to 200 million years after the Big Bang, forming small clusters that gradually merged into larger systems. Large, luminous galaxies were not expected until at least 500 to 700 million years had passed. The galaxies JWST observed did not fit this progression. Many already appeared to have formed dense stellar cores. Their light profiles suggested compact morphologies rather than loosely bound associations of stars. Some even hinted at internal structure, a feature that should require extended periods of dynamical settling. Such order should not exist so early, especially given the turbulent conditions predicted for the young universe. Equally puzzling was the efficiency of gas conversion into stars. For galaxies to reach the observed masses, they would need to convert a significant fraction of their available gas into stars at extraordinary rates. In some cases, star formation rates inferred from ultraviolet luminosities exceeded 50 solar masses per year. For comparison, the Milky Way today forms only 1 to 2 solar masses of stars annually. Achieving such rates so early would require conditions that bypass known cooling and feedback limits. Another challenge came from the implied stellar populations. The light from these galaxies suggested the presence of relatively mature stars, not just the first generation of massive, short-lived stars. That raised questions about how quickly multiple generations of stars could form, evolve, and enrich their surroundings in heavy elements within such a brief cosmic window. While this chemical complexity will be explored later, even the earliest indications pointed to accelerated evolution far beyond expectations. Attempts to reconcile the observations initially focused on uncertainties. Astronomers questioned whether stellar mass estimates might be inflated due to assumptions about the initial mass function of stars. If early galaxies formed a higher proportion of massive stars, they would appear brighter without necessarily being more massive. However, even aggressive adjustments to these assumptions failed to fully resolve the discrepancy. The galaxies still appeared too massive, too bright, and too numerous. The possibility of observational bias was also examined. JWST's unprecedented sensitivity could be preferentially detecting the brightest objects, skewing early impressions. But as surveys expanded and deeper fields were analysed, the pattern persisted. These galaxies were not isolated anomalies. They formed a population that demanded explanation. Theoretical models struggled to adapt. Simulations based on the standard cosmological framework rely on hierarchical growth, where small structures merge to form larger ones over time. This process is inherently gradual. Speeding it up enough to produce billion solar mass galaxies within a few 100 million years requires assumptions that strain the physics of gas, cooling, star formation, and feedback processes. Even when simulations were tuned to maximize early star formation, they rarely matched the observed densities. The tension extended beyond simulations to analytical models of cosmic growth. The rate at which dark matter halos collapse is governed by the expansion history of the universe and the distribution of primordial density fluctuations. Observations from the cosmic microwave background tightly constrain these parameters. There is little room to dramatically accelerate halo formation without conflicting with well-established measurements. Astronomers noted a potential mismatch between theoretical predictions and observational results. While existing models were not formally rejected, the observed properties of these galaxies differed from expectations in both number and apparent maturity. JWST data showed galaxies at early epochs with characteristics not predicted by standard timelines, based on observations made with instrumentation optimized for this wavelength range. These early discoveries prompted further investigation into the timing of galaxy formation and the physical processes active in the early universe. Researchers examined whether star formation proceeded differently under primordial conditions, whether gas cooling mechanisms were more efficient, or whether existing assumptions about dark matter behavior required modification. Each of these possibilities was evaluated in the context of explaining the observed galaxy population. What made these findings especially compelling was that they did not arise from a single controversial observation. Multiple research teams, using independent datasets and analysis methods, reached similar conclusions. As peer-reviewed papers accumulated, the initial surprise hardened into a recognized problem. The early universe appeared more active, more productive, and more structured than theory had predicted. These observations altered expectations about the pace of early galaxy formation. Rather than a gradual build-up of structure, data indicated the presence of complex systems at earlier times than predicted by standard models. The galaxies detected at high redshift highlighted inconsistencies between observation and existing theoretical frameworks, leading researchers to re-examine models of early cosmic epochs, including periods associated with the formation of the first stars. When the universe was supposed to be dark, after the appearance of unexpectedly mature galaxies, attention shifted to the environment in which they were supposedly born. According to established cosmology, the early universe entered a prolonged phase following recombination when light-producing objects were extremely rare. This interval, often described as the cosmic dark ages, began roughly 380,000 years after the Big Bang and extended for hundreds of millions of years. During this time, the universe was filled primarily with neutral hydrogen gas, and there were no stars, no galaxies, and no internal light sources capable of illuminating space on large scales. This darkness was not metaphorical. Neutral hydrogen efficiently absorbs ultraviolet radiation, preventing light from traveling freely. As a result, even the earliest stars, once they formed, were expected to be isolated points struggling against an opaque cosmic fog. Models predicted that it would take a long time before enough radiation accumulated to ionize this hydrogen and allow light to propagate over intergalactic distances. That gradual process is known as cosmic reionization, and it plays a central role in determining when galaxies should become visible. Based on data from the cosmic microwave background and quasar absorption spectra, reionization was thought to begin around 400 million years after the Big Bang and complete by about 1 billion years. This timeline implied that galaxies forming before or during the early stages of reionization would be extremely difficult to detect and intrinsically small. Their growth was expected to be throttled by the very environment they inhabited. Cold gas needed to form stars should have been scarce, and radiation from the first stars should have suppressed further star formation by heating surrounding material. The galaxies identified in the earliest JWST surveys exist squarely within this dark era. Some are observed at times corresponding to only 200 to 300 million years after the Big Bang, well before reionization was thought to be underway in earnest. Yet they are not hidden or weak. They emit enough ultraviolet light to be clearly detected across vast cosmic distances. This implies not only that they existed, but that they were already producing intense radiation capable of piercing through neutral hydrogen. Observations of early luminous galaxies prompted a reassessment of assumptions regarding the opacity of the early universe. Measurements of the Gunn-Peterson trough in quasar spectra indicate that neutral hydrogen dominated the intergalactic medium at high redshift. The detection of bright galaxies at these epochs is consistent with scenarios in which reionization began earlier, progressed more rapidly, or occurred non-uniformly, producing localized regions of ionized gas surrounding early galaxies. Evidence supporting this idea began to emerge from JWST spectroscopy. In several high redshift galaxies, astronomers detected emission lines associated with ionized gas, indicating that these systems were already affecting their surroundings. The size of the ionized regions implied by these signals suggests that early galaxies were not passive objects embedded in darkness, but active agents reshaping the intergalactic medium. Some estimates indicate ionized bubbles tens of thousands of light years across, far larger than expected for such young systems. The presence of these ionized regions has major implications for how galaxies could grow so quickly. Ionized gas cools more efficiently than neutral gas, making it easier to collapse into stars. If early galaxies were able to carve out ionized pockets around themselves, they may have created localized environments favorable to rapid star formation. This would partially explain how galaxies could become massive and luminous, despite forming in an era once thought hostile to growth. Still, This explanation introduces new tensions. Creating and maintaining ionized regions requires a tremendous output of energetic photons. For galaxies to do this so early, they must have hosted large populations of massive stars emitting intense ultraviolet radiation. This, in turn, raises questions about how such stars formed in the first place. The primordial universe lacked heavy elements that facilitate gas cooling, making star formation more difficult. Yet the observations imply that star formation was not only possible, but highly efficient. Observations from the Atacama Large Millimeter, Submillimeter Array added another layer to the puzzle. ALMA detected dust and gas signatures in several early galaxies, suggesting that star formation had already progressed far enough to produce solid particles. Dust formation requires previous generations of stars to live and die, enriching their surroundings through supernova explosions. The presence of dust during the supposed Dark Ages implies that stellar evolution cycles were already well underway. The timing problem becomes even more severe when considering how quickly these processes must have unfolded. From the moment the first stars ignited, galaxies would need to assemble, produce radiation, ionize their surroundings, and begin chemical enrichment within a span of a few tens of millions of years. This compressed timeline challenges existing models that spread these milestones over hundreds of millions of years. Another unexpected detail comes from the spatial distribution of early galaxies. If the universe were uniformly dark and neutral, early galaxies should be isolated and randomly scattered. Instead, some JWST fields reveal clustering, with multiple high redshift galaxies appearing in close proximity. This suggests that structure formation was already advanced enough to produce dense regions capable of hosting multiple luminous systems. Such clustering accelerates reionization locally, amplifying the effects of early light sources. Numerical simulations attempting to reproduce these conditions face significant difficulties. Models that increase early star formation to match observed luminosities tend to overproduce radiation, ionizing the universe too quickly compared to observational constraints. Conversely, models that preserve the traditional reionization timeline fail to generate galaxies bright enough to match what JWST sees. This trade-off highlights a deeper inconsistency between the darkness expected of the early universe and the light now observed. The issue is not confined to a single dataset or telescope. Independent analyses using gravitational lensing, which magnifies distant galaxies through the gravity of intervening clusters, have revealed similar populations of early luminous galaxies. These lensing studies extend detections to even fainter systems, suggesting that the bright galaxies seen directly may represent only the visible tip of a much larger population. These findings are consistent with scenarios in which the cosmic dark ages were spatially non-uniform. Models incorporating early galaxy formation allow for regions of ionized gas interspersed within predominantly neutral hydrogen. Such conditions differ from earlier models that assumed a more uniform and gradual progression of reionization. The growing body of observational evidence has led researchers to reassess assumptions about the timing and extent of early cosmic darkness. Data from high redshift galaxies suggests that light production and ionization may have occurred earlier or more efficiently than predicted by previous models. These observations place constraints on theoretical descriptions of early structure formation and reionization. Further analysis has focused on the internal processes within early galaxies. Even under scenarios that permit earlier light propagation, the inferred star formation rates remain higher than predicted by existing models. Investigating the stellar populations and physical mechanisms responsible for this radiation is necessary to account for the observed luminosities, stars that grew faster than physics allows. Once it became clear that light was present far earlier than expected, the focus narrowed to the source of that light. Galaxies do not shine on their own, their brightness is driven by stars. The problem confronting astronomers was not simply that early galaxies existed, but that they were forming stars at rates that seemed incompatible with the physical conditions of the early universe. The stellar engines inside these galaxies appeared to be running at full power almost from the moment they ignited. Star formation is a complex process that depends on the cooling and collapse of gas clouds. In the present-day universe, this process is regulated by heavy elements such as carbon, oxygen, and silicon, which allow gas to radiate heat efficiently. In the early universe, these elements were essentially absent. Gas consisted almost entirely of hydrogen and helium, making cooling inefficient and slowing the collapse required to form stars. This limitation is one of the core reasons early star formation was expected to be slow and sporadic. Observations now suggest the opposite. Several high redshift galaxies, identified by JWST, show star formation rates exceeding 30 to 100 solar masses per year. In extreme cases, some estimates push beyond 200 solar masses per year. These values rival or exceed those seen in the most intense starburst galaxies in the modern universe, systems often triggered by major mergers and rich in heavy elements. Seeing such activity in a chemically primitive environment was not anticipated. The speed of stellar buildup compounds the issue. Based on spectral energy distributions, some galaxies appear to have formed the bulk of their stars within a time span of less than 100 million years. That means gas must have collapsed, fragmented, and ignited stars with extraordinary efficiency. Theoretical models predict that stellar feedback from the first massive stars, including radiation pressure and supernova explosions, should disrupt surrounding gas and suppress further star formation. Yet in these early galaxies, star formation appears to have continued unabated. JWST's near-infrared spectrograph provided critical insight into this phenomenon. By analysing the light from individual galaxies, astronomers were able to infer the ages of their stellar populations. In several cases, the data suggests the presence of stars tens of millions of years old, indicating that star formation began almost immediately after the first structures formed. This leaves little room for the delays expected from gas cooling and fragmentation constraints. One proposed explanation involves the nature of the first stars themselves. Known as population 3 stars, these hypothetical objects are thought to have been extremely massive, with some estimates placing them above 100 times the mass of the Sunday. Massive stars burn brighter and hotter, producing intense ultraviolet radiation. If early galaxies formed large numbers of such stars, they could generate significant luminosity quickly. However, massive stars also have very short lifespans, often just a few million years, and their violent deaths should inject energy into their surroundings, making sustained star formation difficult. The observed galaxies appear to defy this logic. Their luminosities suggest ongoing star formation rather than brief, isolated bursts. This implies either that feedback mechanisms were less effective than expected, or that gas was being replenished at an extraordinary rate. Some simulations have explored the possibility that cold gas streams from the cosmic web could continuously feed early galaxies, offsetting the disruptive effects of stellar feedback. While this idea shows promise, it requires conditions that may not have been widespread. Another complication arises from the inferred stellar mass distributions. The relative brightness of these galaxies suggests not only the presence of massive stars, but also substantial populations of lower mass stars that live longer and contribute to stellar mass without dominating luminosity. Forming such a balanced population so early requires a rapid transition from the first massive stars to more conventional star formation modes. How this transition could occur within a few tens of millions of years remains unclear. ALMA observations added crucial constraints by detecting cold molecular gas, the raw material for star formation, in several early galaxies. The quantities inferred are surprisingly large, often exceeding 10 billion solar masses. Maintaining such reservoirs while simultaneously forming stars at extreme rates suggests a delicate balance between gas inflow, star formation, and feedback. If any one of these processes dominated, the system would quickly exhaust its fuel or blow it away. The density of star-forming regions also poses a challenge. To achieve the observed rates, gas clouds must collapse efficiently across large volumes. This requires turbulent conditions that compress gas without overheating it. In the local universe, such conditions are often associated with galaxy interactions or mergers. However, many early galaxies show no obvious signs of major mergers, raising questions about what drove such intense star formation. Radiation from early stars further complicates the picture. Ultraviolet photons ionize hydrogen, increasing gas temperature and resisting gravitational collapse. In principle, this should limit star formation in young galaxies. Yet the very presence of sustained star formation suggests that either radiation escaped without strongly coupling to the gas, or that dense regions shielded themselves effectively. Understanding how this balance was achieved is an active area of research. Another piece of evidence comes from the inferred initial mass function of stars in these galaxies. Some analyses suggest a top-heavy distribution, meaning a higher fraction of massive stars than seen today. While this could explain high luminosities, it also intensifies feedback effects, making long-lived star formation harder to sustain. Moreover, even extreme assumptions about the initial mass function fail to fully reconcile observed stellar masses with available time. The rapid buildup of stars also affects the timing of chemical enrichment. Massive stars produce heavy elements through supernova explosions, dispersing them into surrounding gas. Observations indicate that this enrichment process began early, influencing the composition of gas available for subsequent generations of stars. The inferred timescales are shorter than those assumed in traditional models of early star formation. The challenge is not limited to a few exceptional galaxies. Statistical studies indicate that elevated star formation rates were common among early luminous systems. This suggests a global phenomenon rather than isolated extremes. If true, then star formation physics in the early universe may operate under rules that differ significantly from those governing later epochs. Current observations constrain models of early star formation and galaxy evolution. Variations in gas temperature, turbulence influenced by dark matter dynamics, and interactions between radiation and matter are among the factors being examined in simulations to reproduce the observed star formation rates. These parameters remain areas of active investigation. Observations indicate that stars in early galaxies formed on short timescales and contributed significantly to the luminosities detected at high redshift. These stellar populations are associated with galaxies that had already accumulated substantial mass within a few 100 million years of the Big Bang. Examining the mechanisms responsible for rapid mass assembly in these systems is necessary to account for the observed properties. Galaxies more massive than the young universe. Once the speed of early star formation became impossible to ignore, a deeper problem emerged. Even if stars could form rapidly, entire galaxies still needed to accumulate enormous amounts of mass in an extraordinarily short time. Measurements derived from JWST photometry and spectroscopy indicated that some galaxies observed within the first 400 million years after the Big Bang already contained stellar masses exceeding 1 billion solar masses. A few candidates pushed even higher, approaching 10 billion solar masses. These numbers place them in the same mass range as mature galaxies seen billions of years later. Galaxy mass does not appear out of nowhere. Stars form inside dark matter halos, massive gravitational structures that collapse out of the early density fluctuations left behind by inflation. In the standard cosmological framework, these halos grow gradually as smaller halos merge together. This hierarchical growth sets a natural speed limit on how quickly galaxies can become massive. In the early universe, massive halos should have been extremely rare, especially at redshifts greater than 10. The galaxies now observed violate that expectation. Based on the distribution of dark matter predicted by cosmological simulations, the probability of forming enough massive halos to host so many large galaxies at such early times is exceedingly low. Some analyses suggest that the observed number densities are an order of magnitude higher than theoretical predictions. This discrepancy grows larger as observations push to higher redshifts. One of the first attempts to explain this focused on uncertainties in stellar mass estimates. Stellar mass is inferred by modelling how populations of stars emit light over time. Small changes in assumptions about star ages, dust content, or star formation histories can shift mass estimates. However, even when using conservative assumptions that minimize stellar mass, many early galaxies remain uncomfortably massive. Reducing their inferred masses enough to align with models would require assumptions that conflict with observed spectral features. Another possibility is that dark matter halos formed earlier and faster than predicted. However, the growth of halos is tightly constrained by measurements of the cosmic microwave background made by missions such as Planck and WMAP. These observations fix the amplitude of primordial density fluctuations with high precision. There is little flexibility to dramatically increase early halo formation without breaking agreement with these data. Gravitational lensing studies have reinforced the problem. By observing distant galaxies magnified by massive foreground clusters, astronomers can detect fainter and potentially more typical systems at early times. These lensed surveys reveal that massive galaxies are not isolated extremes. Instead, they appear as part of a broader population with unexpectedly high masses. This reduces the likelihood that early JWST detections are statistical outliers. The challenge extends beyond total mass to mass assembly timescales. To reach 1 billion solar masses in stars by 300 million years after the Big Bang, a galaxy must sustain extremely high star formation rates, almost continuously from the moment it begins forming stars. Any significant interruption would make such growth impossible. This leaves little room for the regulatory effects of feedback, which are expected to slow star formation by heating or expelling gas. Simulations attempting to reproduce this rapid mass assembly face persistent difficulties. Increasing star formation efficiency helps, but quickly leads to conflicts elsewhere. Galaxies become too luminous compared to observations at slightly later epochs, or they exhaust their gas too early and stop forming stars prematurely. Fine-tuning parameters can improve agreement in one redshift range, but worsens it in another, suggesting a deeper issue with the underlying assumptions. The spatial distribution of mass within these galaxies adds to the mystery. JWST imaging reveals that many early massive galaxies are compact, with stellar material packed into regions only a few hundred light-years across. Such densities imply intense gravitational binding and rapid dynamical settling. Achieving this level of compactness requires efficient angular momentum loss, a process that usually occurs over extended periods or during major mergers. Yet evidence for widespread major mergers at these epochs is limited. While some galaxies do show disturbed morphologies, many appear surprisingly smooth and centrally concentrated. This suggests that mass was assembled through processes other than frequent, violent collisions. Smooth gas accretion from the surrounding cosmic web has been proposed as an alternative, but this mechanism must operate at unprecedented efficiency to explain the observed masses. The relationship between stellar mass and dark matter, halo mass, further complicates matters. In the local universe, only a small fraction of a halo's mass ends up in stars. Early massive galaxies appear to convert a much larger fraction of their available baryons into stars. In some cases, inferred conversion efficiencies approach or exceed theoretical limits. This raises questions about whether feedback processes were weaker, delayed, or fundamentally different in the early universe. Observations of galaxy clustering offer additional insight. Massive galaxies tend to reside in dense regions of the universe, where dark matter halos grow faster due to enhanced gravitational attraction. Early JWST surveys show hints of such clustering at high redshift, suggesting that some galaxies formed in especially favorable environments. However, even accounting for this effect does not fully explain the abundance of massive systems observed. The mass problem also intersects with the timeline of cosmic reionization. Massive galaxies produce large amounts of ionizing radiation, which can suppress further gas accretion by heating the surrounding medium. If many massive galaxies existed early, reionization should have progressed rapidly. Yet other observations indicate that reionization was still incomplete several 100 million years after the Big Bang. Reconciling these two lines of evidence remains difficult. Researchers have proposed hypotheses, such as alternative dark matter models, that could permit earlier structure formation, or modifications to the expansion history of the universe during its first few 100 million years. These proposals are constrained by observations across multiple cosmological datasets, including galaxy formation, the cosmic microwave background, and large-scale structure. The mass discrepancy appears consistently across multiple observational methods. Photometric analyses, spectroscopic confirmations, and lensing studies independently indicate the presence of massive galaxies at early times. Multiple datasets provide converging measurements of galaxy masses at high redshift. Continued observations are improving constraints on the lower mass end of the galaxy population at high redshift. Preliminary results indicate that smaller galaxies may also have higher stellar masses than previously predicted, suggesting that mass assembly in early galaxies may have occurred more efficiently than model expectations. Observations indicate that some early massive galaxies exhibit ordered rotation and disk-like structures. Measurements of stellar kinematics and morphology suggest that these galaxies had dynamically organized components within the first few 100 million years after the Big Bang. Perfect disks in a chaotic young cosmos. The massive galaxies observed in the early universe presented one puzzle after another, but the next shock came from their structure. Contrary to expectations, several of these galaxies displayed disk-like morphologies, showing surprisingly orderly, rotationally supported shapes in an epoch previously assumed to be dominated by chaotic mergers and turbulence. Before JWST, conventional models predicted that the first few 100 million years would host only irregular, clumpy protogalaxies. Yet now astronomers were finding fully formed, flattened galaxies with evidence of coherent rotation. High-resolution imaging and spectroscopic studies revealed that some of these early disks extended across several thousand light-years and had axial ratios indicating significant flattening. Measurements of Doppler shifts across the galaxies provided evidence for rotational velocities between 70 and 200 kilometers per second. These velocities indicate that the galaxy's gravitational potential was centrally concentrated, and that mass had settled into a stable configuration within the first 500 million years after the Big Bang. Observations at redshifts 10 to 13, corresponding to roughly 300–400 million years after the Big Bang, show that some galaxies have disk-like morphologies. JWST NIRCam images of galaxy JADESGSZ130 display an elongated light profile with a central bulge and disk-like outskirts. Spectroscopic follow-up with NIRSpec indicates a velocity gradient consistent with rotation along the major axis. The smooth light distribution is consistent with stellar populations distributed without large irregular clumps. The formation of such disks, under standard cosmological assumptions, presents significant challenges. Galaxies form within dark matter halos, and their early growth is thought to be driven largely by hierarchical mergers. These mergers are violent events that disrupt gas and stars, producing irregular shapes and turbulent velocity fields. In contrast, the disk galaxies, observed by JWST, exhibit minimal signs of recent mergers. Their rotation curves are smooth, and their stellar populations show age gradients consistent with gradual star formation rather than bursts induced by collisions. One explanation involves cold flow accretion, where filamentary streams of cold hydrogen gas funnel into galaxies along the cosmic web. Unlike gas heated during mergers or shocks, cold flow gas can settle into a rotating disk, preserving angular momentum and allowing ordered star formation. Simulations have suggested that cold flows could contribute to disk formation, but achieving the degree of rotational coherence observed remains difficult. In particular, the disks appear dynamically thin, meaning that vertical support against gravity is primarily provided by rotation rather than turbulent pressure. Producing thin disks in less than 400 million years pushes the limits of current models. The chemical composition of these early disks adds further complexity. Spectroscopic measurements have detected oxygen, carbon, and nitrogen in some of these galaxies, indicating that multiple generations of star formation had already occurred. This enrichment allows gas to cool more efficiently, promoting disk formation, but it also implies an accelerated stellar evolution history. In order to form both massive stars and longer-lived lower mass stars, the disks must have maintained a delicate balance between gas inflow, star formation, and feedback. Observations with ALMA of molecular gas in galaxies such as MAX 1149JD1 reveal cold gas reservoirs exceeding several billion solar masses, concentrated within disk-like structures, suggesting that the material needed for continued disk growth was abundant. Another striking aspect is the compactness of these disks. Some early disk galaxies have effective radii of only 300 and 500 light-years, while containing stellar masses exceeding 1 billion solar masses. The resulting stellar densities are several hundred times higher than those of the Milky Way's disk. Achieving such densities requires rapid angular momentum transport to allow mass to settle toward the center while maintaining rotational support. Mechanisms for this include gravitational torques from spiral arms, bars, or clump migration. But whether these processes could operate effectively at such early times is uncertain. Kinematic studies also reveal that rotational support in these galaxies was dominant. In several JWST targets, the ratio of rotation velocity to velocity dispersion exceeds 3. indicating that ordered motion outweighs random turbulence. This contrasts sharply with expectations for early massive galaxies, where simulations predict turbulence-driven support, velocity dispersions exceeding rotation, and irregular velocity fields. The presence of rotationally dominated systems so early suggests that angular momentum must have been preserved efficiently during collapse, challenging assumptions about the chaotic nature of early star formation. Surveys of JWST deep fields show that a substantial fraction of massive galaxies at redshifts 1013 exhibit disk-like features. Initial estimates suggest that up to 30% of these galaxies have well-ordered morphologies. The observed prevalence of disks may indicate that smooth accretion played a significant role in early mass assembly. Interestingly, some of the disks also display clumpy star-forming regions reminiscent of giant HII regions in modern galaxies. These clumps contain stars forming at rates of tens of solar masses per year and are embedded within the disk rather than distributed chaotically. The coexistence of clumpy star formation and overall rotational order suggests that feedback from massive stars did not significantly disrupt the disk, pointing to either unusually efficient gas replenishment or weaker than expected feedback. In the local universe, disk galaxies follow relationships linking rotation velocity, stellar mass, and size. Early disks observed by JWST appear to roughly follow similar trends. This may indicate that the scaling relations of rotation, mass, and size were already emerging at redshifts above 10. Observations indicate that well-ordered disks existed within the first 500 million years after the Big Bang. These galaxies combine high stellar mass, rotational support, chemical enrichment, and active star formation. The processes enabling disk formation may have included angular momentum preservation and smooth accretion, though further study is required to determine their relative contributions. Observations of early disk galaxies show systems with high stellar mass, rotational coherence, and chemical enrichment within the first 500 million years. JWST continues to uncover examples of such disks, providing data on galaxy morphology, kinematics, and chemical composition in the early universe, the heavy elements that shouldn't be there yet. One of the most striking surprises from JWST observations of early galaxies is their chemical maturity. Spectroscopy reveals significant amounts of oxygen, carbon, and nitrogen in galaxies formed less than 500 million years after the Big Bang. These elements, collectively known as metals in astronomical terminology, are produced in the cores of stars and dispersed into the surrounding gas through supernova explosions. Their presence so early challenges conventional timelines, which predict that only the first generation of stars, metal-free population 3 stars, should have existed at these epochs. Detailed measurements of rest frame ultraviolet emission lines, such as OII 5007 and CII 1909, indicate metallicities ranging from 10 to 30% of the solar value in several high redshift galaxies. For comparison, the Milky Way's interstellar medium has a metallicity approximately equal to the solar value. Observations at redshifts 1013, less than 400 million years after the Big Bang, show enrichment consistent with multiple generations of stars having contributed metals within tens of millions of years. ALMA observations of molecular gas support these findings. Carbon monoxide and ionized carbon emission lines have been detected in several high redshift systems, revealing dense gas reservoirs already enriched with metals. These measurements show gas phase metallicities consistent with those inferred from JWST spectra, confirming that the chemical maturity is not an artifact of stellar light modelling. The detection of molecular species also indicates that cooling processes were already efficient, allowing gas to collapse into stars more effectively than previously assumed. Nitrogen is produced primarily in intermediate mass stars through the CNO cycle. Its abundance in galaxies at redshifts above 10 indicates that some stars had time to evolve over hundreds of millions of years, despite the universe being only about 400 million years old. This suggests that star formation occurred rapidly after the first generation of stars, reducing the interval between population 3 and subsequent generations. In addition to absolute abundances, abundance ratios provide information on early stellar populations. The ratio of oxygen to carbon is higher than conventional models predict for early galaxies, consistent with initial mass functions skewed toward very massive stars capable of producing oxygen efficiently. Observations suggest some stars had masses exceeding 100 solar masses, heavier than typical stars today. Top-heavy populations would accelerate chemical enrichment under early conditions. Supernova feedback from early generations injects energy and momentum into surrounding gas. Some galaxies with high metallicity also show ongoing star formation rates above 50 solar masses per year. This indicates that these systems retained enriched gas while continuing to accrete material, contrary to expectations from conventional models. Some early galaxies show carbon-to-oxygen ratios higher than predicted. High carbon abundance suggests that asymptotic giant branch stars had already contributed to the interstellar medium through stellar winds. These stars require tens to hundreds of millions of years to evolve, indicating that star formation in these systems began early and proceeded at a rapid pace. The presence of metals has implications for dust formation. Infrared observations indicate dust grains, likely formed in supernova ejecta. Dust facilitates cooling and molecule formation, enabling star formation. JWST mid-infrared photometry of several Z is greater than 10 galaxies, shows continuum emission consistent with warm dust at temperatures of 40-60 Kelvin, suggesting that a significant fraction of metals has condensed into solid grains. Chemical evolution models assume metal enrichment occurs gradually over hundreds of millions of years. Galaxies at redshifts 10-13 show metallicities approaching 1/3 of solar, suggesting rapid enrichment. Some models propose star formation efficiencies of 50% or more in early systems, compared to the typical 5-10% in later galaxies. High efficiencies could accelerate enrichment, but may conflict with observed gas masses and stellar densities. The diversity of chemical abundances reflects environmental variation. Some high redshift galaxies show metallicities as low as 5% of solar, while others exceed 30% at similar redshifts. Local conditions, gas density, inflow rate, and initial halo mass appear to influence enrichment processes, producing regions with rapid star formation and enrichment alongside less evolved regions. Observationally, heavy element signatures are not confined to the most massive galaxies. Systems with stellar masses below 1 billion solar masses exhibit detectable oxygen and carbon lines. In several JWST fields, low-mass galaxies show metallicities comparable to larger systems, indicating that metal production and retention occurred across a broad range of halo masses. Metals cool gas efficiently, promoting star formation and increasing ultraviolet output. Galaxies with high metallicity could contribute to ionizing radiation during reionization. Observations indicate that reionization was still ongoing at Z to 7-8, showing that enrichment, star formation, and photon escape occurred simultaneously. Some models propose population 3 stars with short lifespans and high yields, or early galactic winds transporting metals over large distances, enriching neighbouring systems. These scenarios are under investigation to explain early metal abundances and chemical enrichment timescales. Observations of massive, disk-like galaxies with high metallicity show that rapid star formation, gas accretion, chemical enrichment, and structural settling occurred simultaneously in the first few 100 million years. These data indicate that some early galaxies were chemically and structurally advanced. Galaxies less than 400 million years old show the presence of oxygen, carbon, nitrogen, and dust. These observations indicate that early star formation produced chemical enrichment and dust formation within the first few 100 million years after the Big Bang. Supermassive black holes without enough time. The story of the early universe becomes even more bewildering when we consider supermassive black holes. Quasars, powered by black holes with masses exceeding 1 billion solar masses, have been detected at redshifts above 7, less than 700 million years after the Big Bang. These cosmic behemoths present a fundamental timing problem. According to conventional physics, there is simply not enough time for a black hole to grow from a stellar mass seed to billions of solar masses under standard accretion rates. Their existence pushes the limits of what we understand about black hole formation, accretion physics, and early galaxy evolution. Observational data from multiple telescopes, including JWST, ALMA, and the Sloan Digital Sky Survey, confirm the presence of several early quasars. One example, ULAS J 1342 plus 0928 at redshift 7.54, hosts a black hole with an estimated mass of 800 million solar masses. Its luminosity exceeds 14 times that of the Sun, indicating an accretion rate near the Eddington limit, the maximum rate at which gravity can overcome radiation pressure to allow matter to fall into a black hole. Growing from a 100 solar mass stellar black hole to nearly 1 billion solar masses in under 700 million years would require sustained accretion at high rates. In the standard seed model, black holes form as remnants of population 3 stars, with initial masses ranging from tens to a few hundred solar masses, and grow through accretion and mergers over hundreds of millions to billions of years. Observed early quasars suggest either unusually massive initial seeds, accretion rates above classical limits, or both. Some models propose direct collapse black holes with initial masses of 4 to 10, 6 solar masses forming from pristine gas clouds, which could reduce the required growth time. Spectroscopic observations of early supermassive black holes show broad ultraviolet emission lines such as MGII and CIV, indicating gas velocities of several thousand kilometers per second. These velocities trace the gravitational influence of the central black hole. In some quasars, the metallicity of the broad line region is comparable to or higher than solar, indicating chemical enrichment occurred during black hole growth. ALMA observations show that some early quasars are in gas-rich environments, with reservoirs exceeding 10 solar masses, providing fuel for rapid accretion. Gas inflow must occur without being expelled by feedback from supernovae or the black hole. Some quasars host dust masses on the order of 8 solar masses, indicating that dust formation, star formation, and black hole growth occurred concurrently. Many early quasars are in massive galaxies, with stellar masses exceeding 10 solar masses. The black hole to stellar mass ratios are higher than in present-day galaxies, sometimes by an order of magnitude, indicating that black hole growth may have been faster than stellar assembly in some early systems. Accretion physics limits black hole growth due to radiation pressure, while feedback from the black hole heats and expels surrounding gas. Some models propose super Eddington accretion, where black holes grow faster than classical limits, possibly through anisotropic inflows or photon trapping. Observations show rapid variability in quasar luminosities, which may indicate episodes of enhanced accretion. Early galaxies experienced frequent mergers, which could funnel gas into central regions to feed black holes. The early universe had high turbulence and feedback, making continuous, stable accretion difficult. Achieving billion solar mass black holes at redshifts above 7 would require multiple mergers and sustained accretion. Quasars emit ultraviolet photons capable of ionizing neutral hydrogen. Surveys indicate that the number density of luminous quasars at Z is greater than 7 is low, suggesting that stars were the primary contributors to global reionization. Some early quasars formed in regions where black holes, stars, and galaxies coexisted in dense environments. Host galaxy kinematics show that some galaxies with early supermassive black holes have rotation curves and gas velocity dispersions consistent with organized motion. These galaxies resemble disk-like systems observed in previous chapters, indicating that some supermassive black holes formed in relatively ordered environments. Gravitational lensing studies reveal fainter early quasars, showing that smaller yet massive black holes existed alongside the most luminous quasars. These observations indicate that supermassive black holes formed in multiple early galaxies, providing constraints for models of early black hole growth within the first 700 million years. Supermassive black holes in the early universe have masses, accretion rates, and host environments indicating rapid growth. Observations show chemically enriched gas, massive host galaxies, and ordered kinematics coexisting in these systems, providing constraints on early black hole formation, galaxy assembly, and star formation. Galaxies brighter than their dark matter halos. The early universe continues to confound astronomers when we examine the relationship between galaxy luminosity and the underlying dark matter thought to host them. In the standard cosmological model, galaxies form within massive dark matter halos, which dominate the gravitational potential and regulate baryonic processes such as gas accretion, star formation, and feedback. There is an expected correlation. More massive halos produce more stars and, therefore, brighter galaxies. Yet JWST and ALMA observations have uncovered galaxies that appear far too luminous for the inferred mass of their dark matter halos, violating one of the fundamental assumptions of galaxy formation. Deep field surveys with JWST's NIRCam have revealed several galaxies at redshifts 9-12 whose ultraviolet luminosities exceed theoretical limits for their expected halo mass. For instance, GNZ11, long known from Hubble observations and now confirmed by JWST, shines with a UV luminosity of approximately 10-11 solar luminosities. Yet its halo, inferred from abundance matching, is only on the order of 10-11 to 10-12 solar masses. According to LCDM predictions, halos of this mass should host galaxies significantly fainter, suggesting that these galaxies have converted a much higher fraction of baryons into stars than expected, or that the halo mass itself is underestimated. One approach to probe the dark matter content is gravitational lensing. Observations of lensed high redshift galaxies, such as those behind the galaxy cluster SMACS J723, allow astronomers to estimate the halo mass by analyzing distortions in background light. In several cases, the stellar mass and luminosity of the galaxy appear inconsistent with the lensing-derived halo mass. These galaxies shine so brightly that either star formation efficiency was extraordinarily high, sometimes exceeding 50% of the available baryons, or our assumptions about halo growth at early times are incomplete. ALMA observations of gas dynamics provide complementary insights. By measuring rotational velocities and velocity dispersions of molecular gas, astronomers can estimate the total gravitational mass within the central few kiloparsecs of a galaxy. Surprisingly, in many early galaxies, the dynamical mass inferred from gas kinematics is lower than would be needed to sustain the observed luminosity if standard stellar population models are assumed. This indicates that either the stars are unusually massive, the initial mass function was skewed toward massive stars, or dark matter is somehow underrepresented in the central regions. For example, the galaxy JADESGSZ 100 shows a rotation velocity of only 80 km per second, yet its UV luminosity suggests a stellar mass of roughly 3 × 10⁹ solar masses, exceeding predictions for a halo of its size. These luminous galaxies also display extremely high star formation rates, sometimes exceeding 100 solar masses per year. Such rapid star formation would normally trigger strong feedback from supernovae and stellar winds, which should blow gas out of the shallow potential wells of modest mass halos. Yet the galaxies retain substantial molecular gas reservoirs, indicating that either feedback is less efficient than models suggest, or gas inflows from the cosmic web are exceptionally rapid. Observations of CO and CII emission lines in these systems suggest that gas depletion times are on the order of 100–200 million years, much shorter than predicted for galaxies in low-mass halos. The brightness to halo mass discrepancy also has implications for cosmic reionization. Bright galaxies in relatively low-mass halos would contribute disproportionately to the ultraviolet photon budget, accelerating reionization in their local environments. This could partially explain the patchiness of early reionization inferred from quasar absorption spectra, where some regions appear ionized earlier than expected. If luminous, halo-like galaxies were common, they may have acted as concentrated sources of ionizing radiation, producing localized bubbles of ionized hydrogen. Some researchers have suggested that these galaxies may host unusually top-heavy initial mass functions, producing more massive, short-lived stars that dominate the luminosity while contributing less to long-term stellar mass. Observations of nebular emission lines support this idea, showing strong ionization states consistent with extremely hot, massive stars. This would temporarily boost the galaxy's brightness, but it cannot fully account for the systematic overluminosity observed across multiple systems. The consistency of the effect suggests a more fundamental tension between halo mass and stellar assembly in the early universe. Dark matter itself may be implicated. The standard cold dark matter model predicts a hierarchical growth pattern, with small halos merging into larger ones and galaxies forming gradually. If the early universe contained a population of halos with unusual properties such as higher concentrations or non-standard density profiles, then star formation could proceed more efficiently than expected. Some simulations exploring alternative dark matter candidates, like warm dark matter or self-interacting dark matter, produce halos that allow faster baryonic collapse, potentially explaining over-luminous galaxies. However, these models remain speculative and must simultaneously satisfy constraints from large-scale structure and the cosmic microwave background. The environment also plays a role. Observations suggest that overluminous galaxies often reside in modest density regions rather than in the most massive protoclusters. This contradicts the expectation that extreme luminosity should correlate with high-density, high-mass halos. Instead, these galaxies appear to thrive in environments where halo mass is not the dominant limiting factor, implying that local gas accretion rates and internal dynamics may outweigh halo mass in regulating star formation during the first 500 million years. High-resolution imaging from JWST further reveals that many overluminous galaxies have surprisingly compact morphologies. Half-light radii are typically 300–600 parsecs, yet the stellar masses inferred from their brightness reach billions of solar masses. Such compact, luminous systems place extreme demands on star formation efficiency, implying that gas must have been converted into stars at rates far exceeding those assumed in cosmological simulations. The combination of compactness and brightness underscores the tension between observation and theoretical expectations. Some of these galaxies also exhibit unexpectedly mature stellar populations. Spectroscopic modelling indicates ages of 150–300 million years for a substantial fraction of stars in systems observed at redshifts above 10. This suggests that star formation began almost immediately after the first galaxies collapsed, providing sufficient time for the observed luminosity while still challenging the assumed halo mass-to-light ratio. The rapid assembly of both stars and metals in these galaxies indicates a degree of coordinated growth that is difficult to reproduce in simulations using standard LCDM parameters. JWST surveys are revealing a growing number of galaxies whose luminosity exceeds predictions for their halo mass. These systems are observed across multiple fields and redshift ranges, indicating that overluminosity relative to inferred halo mass occurs repeatedly in the early universe. Observational analyses point to either elevated star formation efficiency in low-mass halos, or deviations from standard assumptions about halo mass assembly and baryon conversion during the first 500 million years. Observations have identified galaxies in the early universe that combine extreme ultraviolet luminosity, high star formation rates, compact morphologies, and, in some cases, relatively mature stellar populations, despite being associated with dark matter halos of modest inferred mass. These properties are measured through deep JWST imaging, spectroscopic modelling, and complementary ALMA observations. Ongoing surveys continue to expand the sample of such systems across a range of redshifts, providing additional observational constraints on star formation, gas accretion, and halo growth during the earliest stages of galaxy assembly, the galaxies that ignored hierarchical growth. For decades, hierarchical growth has been a cornerstone of galaxy formation theory. In this framework, small structures form first, then merge repeatedly to build larger galaxies over cosmic time. The earliest universe, especially within the first 500 million years, was expected to be dominated by fragmented systems still in the process of assembly. Yet a growing number of galaxies observed by JWST appear to have bypassed this step-by-step construction entirely. Instead of showing evidence of gradual build-up through mergers, these galaxies appear suddenly, already massive, coherent, and largely complete. JWST deep field surveys, such as JADES, SEERS, and PRIMA, have revealed galaxies at redshifts between 9 and 13, whose stellar masses exceed several billion solar masses. What makes these systems unusual is not only their mass, but the apparent lack of smaller precursor components in their immediate surroundings. If hierarchical growth were operating as expected, astronomers would anticipate a population of merging satellites, tidal debris, or irregular substructures. Instead, many of these galaxies appear isolated, smooth, and structurally unified, suggesting that their mass assembled through mechanisms other than repeated mergers. High-resolution imaging has been particularly revealing. JWST's angular resolution allows astronomers to resolve structures on scales of a few hundred parsecs at these redshifts. In several massive early galaxies, the light distribution is continuous and centrally concentrated, with no obvious signs of recent accretion events. The absence of asymmetric features, stellar streams, or multiple nuclei challenges the idea that these systems were built through successive mergers of smaller galaxies. In contrast, simulations based on LCDM predict frequent mergers at these epochs, producing visibly disturbed morphologies. Spectroscopic evidence reinforces this picture. Velocity maps derived from emission lines show smooth gradients rather than the kinematic chaos expected from recent mergers. In systems like JADES-GSZ111, gas and stars appear dynamically settled, with rotation-dominated motion and relatively low velocity dispersion. Such kinematic coherence implies that the galaxy has had sufficient time to relax gravitationally, a process that typically follows mergers by hundreds of millions of years. Given the age of the universe at these redshifts, this relaxation should not have been possible if hierarchical growth dominated. Comparisons with cosmological simulations highlight the discrepancy. State-of-the-art simulations such as Illustris TNG and Eagle predict that galaxies above 1 billion solar masses at redshifts greater than 10 should be exceedingly rare and almost always accompanied by evidence of recent mergers. Yet JWST observations suggest that these galaxies are more common than predicted, and many show no merger signatures at all. Attempts to tune simulation parameters, such as increasing star formation efficiency or reducing feedback strength, have improved mass estimates but failed to reproduce the observed absence of hierarchical assembly features. One proposed alternative involves smooth, rapid gas accretion from the cosmic web. In this scenario, galaxies grow primarily by drawing in gas along dense filaments rather than through discrete mergers. This gas can flow directly into the central regions, fueling intense star formation and rapid mass buildup without leaving the structural scars associated with mergers. Observational hints of this process come from the alignment of some galaxies with large-scale filamentary structures inferred from surrounding galaxy distributions. However, the efficiency required to assemble billions of solar masses so quickly remains difficult to reconcile with existing models. Environmental studies further complicate the picture. Some of the most massive early galaxies are found in relatively average density regions rather than in the densest protoclusters where hierarchical growth should be most active. This suggests that their rapid assembly was not driven by an abundance of merger opportunities. Instead, internal processes and sustained gas inflow may have dominated their evolution. The presence of massive, apparently self-assembled galaxies in such environments challenges the assumption that dense regions are the primary sites of early massive galaxy formation. The stellar populations of these galaxies provide additional clues. Spectral energy distribution modeling indicates that many of these systems contain stars spanning a range of ages rather than a single burst population. This suggests continuous star formation over tens or hundreds of millions of years, inconsistent with the episodic bursts expected from merger-driven growth. The smooth buildup of stellar mass implied by these age distributions supports the idea that these galaxies grew steadily rather than hierarchically. Another notable aspect is the uniformity of these galaxies' properties. Across different fields and redshifts, massive early galaxies show similar sizes, masses, and star formation rates. Under hierarchical growth models, merger histories are expected to vary substantially, leading to a broader dispersion in observable properties. The observed consistency indicates that these galaxies formed under comparable physical conditions across multiple environments in the early universe. The lack of smaller building blocks also affects our understanding of galaxy demographics. Hierarchical models predict a steep increase in the number of low-mass galaxies at high redshift, many of which should later merge into larger systems. While JWST does detect numerous low-mass galaxies, their numbers and properties do not fully account for the mass contained in the most massive systems observed. This mismatch suggests that a significant fraction of stellar mass appeared in large galaxies without passing through a prolonged low-mass phase, contradicting the bottom-up paradigm. Some researchers have explored whether observational biases could explain the discrepancy. For instance, mergers between very small, faint galaxies might escape detection even with JWST. However, simulations incorporating JWST's sensitivity indicate that mergers massive enough to build billion solar mass galaxies should leave detectable signatures. The continued absence of such signatures across multiple independent surveys makes observational bias an unlikely sole explanation. The presence of massive galaxies at very high redshift affects interpretations of early structure formation. Observations indicate that some galaxies reach large stellar masses within the first few 100 million years, under conditions where hierarchical assembly models predict slower growth. These systems provide constraints on gas cooling, angular momentum transport, and baryon dark matter interactions during early galaxy formation. JWST observations continue to identify galaxies at high redshift whose masses, morphologies, and kinematic properties show limited evidence for recent merger-driven assembly. These systems exhibit rapid stellar mass growth, coherent internal structure, and sustained star formation at early cosmic times. The expanding sample provides additional observational data for evaluating the role of mergers, gas accretion, and internal processes in early galaxy growth. Star factories in the wrong neighborhoods. As the picture of early galaxy formation continues to unravel, another unexpected pattern emerges. Some of the most extreme star-forming galaxies in the early universe are found in environments where star formation should have been suppressed. According to long-standing models, the most intense bursts of star formation should occur in dense regions of the cosmic web, where frequent interactions, abundant gas, and deep gravitational potentials promote rapid growth. Instead, JWST and ALMA are revealing galaxies, producing stars at astonishing rates in comparatively low-density regions, far from the crowded neighborhoods where theory predicts they belong. Environmental reconstructions of the early universe rely on mapping galaxy distributions across deep fields. Using JWST's unprecedented sensitivity, astronomers can now identify faint companion galaxies and infer local density contrasts even at redshifts above 8. These studies show that several galaxies with star formation rates exceeding 50 to 150 solar masses per year are located in regions with few nearby neighbors. In some cases, the nearest comparable galaxy lies tens of thousands of light-years away, a significant distance given the compact nature of early cosmic structures. This isolation runs counter to the idea that dense protoclusters were the primary engines of early star formation. One striking example comes from the CEERS survey, which identified a galaxy at redshift 9.1 forming stars at nearly 120 solar masses per year. Despite its extreme activity, follow-up analysis found no surrounding overdensity of galaxies that would indicate a proto-cluster environment. Similar results have emerged from the JWST field, where multiple high redshift starbursts appear embedded in relatively average or even underdense regions of the early universe. These findings suggest that intense star formation was not exclusively tied to the environment in the way models predict. Theoretical expectations are rooted in the relationship between environment and gas supply. In dense regions, gravitational potentials are deeper, allowing halos to capture and retain cold gas more effectively. In lower density regions, gas accretion should be slower, and feedback from star formation should more easily expel gas, suppressing sustained starbursts. Yet observations indicate that some isolated early galaxies maintained abundant cold gas reservoirs, fueling prolonged and extreme star formation despite their apparent environmental disadvantage. ALMA has played a critical role in revealing this contradiction. Observations of CII and CO emission lines in these isolated starburst galaxies show molecular gas masses ranging from several billion to over 10 billion solar masses. These reservoirs are comparable to those found in galaxies located in much denser environments. Moreover, gas surface densities inferred from these observations are extremely high, supporting star formation efficiencies that rival or exceed those of later cosmic starbursts. The presence of such dense gas in low-density regions challenges assumptions about how gas is delivered and retained in the early universe. One possible explanation involves the structure of the cosmic web itself. Even in regions that appear underdense in terms of galaxy counts, narrow but dense filaments of gas may feed individual galaxies efficiently. These filaments can channel cold gas directly into galactic centers, sustaining star formation without the need for frequent mergers or a crowded environment. While simulations do predict filamentary accretion, the efficiency required to support star formation rates above 100 solar masses per year in isolated systems is significantly higher than predicted. The internal conditions of these galaxies also appear unusual. Spectroscopic measurements reveal high ionization parameters and strong nebula emission lines, indicating intense radiation fields produced by massive stars. In several cases, the inferred ages of dominant stellar populations are less than 50 million years, suggesting either extremely recent onset of star formation or repeated closely spaced bursts. Maintaining such activity without environmental reinforcement implies a level of internal regulation that current models struggle to reproduce. Another surprise lies in the apparent lack of suppression mechanisms. In low-density environments, feedback from supernovae and stellar winds should more easily disrupt gas clouds, halting star formation. However, observations suggest that feedback in these early star factories was either inefficient or quickly counteracted by fresh gas inflow. High-resolution JWST imaging shows compact star-forming regions deeply embedded within dense gas, potentially shielding them from disruptive feedback. This configuration could allow star formation to proceed unabated even in shallow gravitational potentials. The mismatch between environment and star formation also has implications for galaxy clustering statistics. If intense star formation can occur in isolation, then early galaxy populations may be less biased toward dense regions than previously assumed. This affects interpretations of large-scale structure measurements and challenges the use of star-forming galaxies as tracers of underlying dark matter distributions at high redshift. Early results suggest that star formation activity may have been more evenly distributed across environments than models predict. Comparisons with simulations underscore the tension. In most LSEDM-based simulations, extreme star formation at redshifts above 8 is strongly correlated with overdense regions and massive halos. Attempts to reproduce isolated starbursts require artificially boosting gas accretion rates or suppressing feedback, often leading to conflicts with other observed properties, such as galaxy sizes or metallicities. The persistence of the discrepancy across multiple observational datasets suggests that the issue lies not in individual assumptions, but in the broader framework linking environment to star formation. These isolated star-forming galaxies contribute to measurements of the total star formation rate density at high redshift. Observational estimates indicate that a portion of early star formation occurred in galaxies located outside of dense protocluster environments. This distribution affects assessments of how star formation activity was spatially correlated with large-scale structure during the first few 100 million years. Some isolated starburst galaxies show evidence of rapid chemical enrichment and dust formation, indicating sustained star formation over timescales sufficient to alter the interstellar medium. Observations of metal lines and infrared emission suggest that these processes occurred despite the absence of dense surrounding environments. These measurements place constraints on how early galaxies acquired, retained, and processed gas under low-density conditions. Ongoing JWST and ALMA observations continue to identify galaxies with extreme star formation rates in low-density environments at high redshift. These systems exhibit large, cold gas reservoirs, compact star-forming regions, and sustained star formation activity despite limited nearby galaxy populations. The growing observational sample provides additional data for evaluating the relationship between environment, gas supply, and star formation during the earliest stages of galaxy evolution. The cold gas that should have disappeared. The discovery of extreme star formation in unlikely environments naturally raises the next question: where did the fuel come from, and why was it still there? In the early universe, intense radiation fields, supernova explosions, and growing black holes were expected to heat, ionize, or expel cold gas rapidly. Yet, observations now reveal that many early galaxies retained vast reservoirs of cold molecular gas, the very material required to form stars, long after models predict it should have vanished. This persistence of cold gas under hostile conditions presents one of the most direct challenges to conventional ideas about early galaxy evolution. ALMA has been central to uncovering this mystery. Observations of CIE, 158 micron emission and carbon monoxide transitions in galaxies at redshifts between 7 and 12 indicate molecular gas masses ranging from a few billion to more than 10 billion solar masses. These values rival or exceed those seen in present-day star-forming galaxies, despite the early universe being far more energetic and compact. In systems such as JADE SGSZ 701 and MAX 1149 JD1, the inferred cold gas mass is comparable to or greater than the stellar mass, implying that these galaxies were still gas-dominated even after significant star formation had already occurred. The survival of cold gas is unexpected because early galaxies experienced intense ultraviolet radiation from massive stars. Such radiation should heat surrounding gas and suppress molecule formation. Additionally, supernova rates were high, injecting energy into the interstellar medium and driving turbulence. In shallow gravitational potentials, this combination should have expelled gas into intergalactic space. Yet velocity-resolved ALMA data show relatively narrow line widths in several early galaxies, indicating that large fractions of their gas remained cold and dynamically settled rather than violently stirred or blown out. Gas depletion times provide another clue. By comparing star formation rates with molecular gas masses, astronomers estimate how quickly galaxies should exhaust their fuel. In many early systems, depletion times are remarkably short, on the order of 100 million years or less, yet the gas reservoirs persist across multiple observed epochs. This implies that gas was either replenished continuously or shielded from destruction more effectively than models predict. The idea of continuous replenishment through cold accretion has been proposed, but sustaining such inflow rates while avoiding heating remains difficult to explain. Observations suggest that the structure of the gas itself may have played a role. High-resolution ALMA imaging reveals that cold gas in early galaxies is often concentrated into dense, compact regions with surface densities far exceeding those in typical later galaxies. These dense clouds can self-shield against ultraviolet radiation, preserving molecular hydrogen even in harsh radiation fields. In galaxies like GNZ11, inferred gas surface densities are several thousand solar masses per square parsec, creating environments where cooling can outpace heating despite intense stellar feedback. The chemical composition of the gas also matters. As discussed earlier, many early galaxies show significant metal enrichment. Even modest amounts of carbon and oxygen dramatically enhance cooling efficiency by enabling fine structure line emission. This allows gas to radiate away energy more effectively, counteracting heating from stars and supernovae. In this sense, rapid chemical enrichment may have inadvertently protected cold gas, allowing star formation to continue rather than shutting itself off. However, achieving both high metallicity and large cold gas reservoirs so early remains a paradox, since star formation consumes gas while producing metals. Another factor is dust. Infrared observations indicate that some early galaxies already contained substantial dust masses, possibly formed in supernova ejecta. Dust grains catalyze the formation of molecular hydrogen and provide additional shielding against radiation. In galaxies observed at redshifts above 8, dust-to-gas ratios appear lower than in the Milky Way, but still high enough to influence gas physics significantly. The presence of dust so early suggests that the interstellar medium evolved rapidly into a state where cold gas could survive longer than expected. The spatial distribution of cold gas offers further surprises. Rather than being dispersed by feedback, gas often appears centrally concentrated, aligned with stellar disks or compact star-forming regions. In several systems, gas kinematics show ordered rotation rather than chaotic motion, indicating that the gas was not repeatedly disrupted. This stability implies that feedback processes were either highly directional or less effective at coupling energy into the dense gas phase. Some simulations suggest that early feedback may have escaped along low-density channels, leaving dense gas relatively unscathed. Environmental context again complicates the picture. Some galaxies with abundant cold gas reside in low-density regions, where external pressure from surrounding material is minimal. In such environments, gas should be even more vulnerable to loss. Yet these galaxies retain cold reservoirs comparable to those in denser regions. This suggests that internal processes, such as gravitational confinement by compact mass distributions, played a dominant role in gas retention. In effect, the galaxy's own rapid mass assembly may have created deep enough potential wells to hold on to gas despite their overall halo mass. The persistence of cold gas also has implications for early black hole growth. Accretion onto central black holes requires dense, cold material, and the presence of large gas reservoirs could explain how some black holes grew so rapidly. However, black hole activity also produces energetic radiation and outflows that should heat or expel gas. Observations of early galaxies hosting active nuclei, yet still rich in cold gas, suggest a delicate balance between feeding and feedback, one that allowed gas to survive in close proximity to powerful energy sources. Attempts to reconcile these observations with theory have prompted revisions to feedback prescriptions in simulations. Some models now incorporate delayed cooling, clumpy gas distributions, or reduced coupling between feedback energy and dense gas. While these adjustments can help preserve cold gas, they often lead to other discrepancies, such as overproducing stars or failing to reproduce observed galaxy sizes. The difficulty of simultaneously matching gas content, star formation rates, and structural properties highlights the complexity of the problem. Measurements of cold gas, mass, and star formation rates indicate that some early galaxies maintained star-forming activity over extended timescales. Observed gas reservoirs and inferred depletion times suggest that star formation was not limited to a single, brief episode in these systems. These properties are consistent with sustained gas availability during early stages of galaxy evolution. JWST and ALMA observations have detected cold molecular gas in a growing number of galaxies across a range of redshifts and environments. These detections include systems with varying star formation rates, masses, and local densities. The expanding dataset provides constraints on heating, cooling, feedback, and gas accretion processes during the first few 100 million years of cosmic history. Cold molecular gas has been detected in early galaxies under conditions where theoretical models predict rapid heating or removal. These galaxies retain sufficient gas to support continued star formation and mass growth despite intense radiation fields and feedback. Observations of gas content and distribution provide input for evaluating models of early galaxy structure and evolution. Galaxy sizes that defy expansion models, with abundant cold gas sustaining star formation far longer than expected, astronomers naturally turn to another fundamental property of early galaxies: their physical size. Under standard cosmological assumptions, galaxies forming in the early universe should be compact, gradually growing larger over time as they accrete mass and angular momentum. Cosmic expansion, halo growth, and mergers all contribute to this slow increase in size. Yet JWST observations are revealing a population of early galaxies whose dimensions are either far too small or surprisingly large for their age, challenging the models that link galaxy size directly to cosmic time and expansion. High-resolution imaging from JWST's NIRCam has enabled precise size measurements for galaxies at redshifts above 8. What immediately stood out was the extreme diversity. Some galaxies, with stellar masses exceeding 1 billion solar masses, have effective radii of only 200 to 400 light-years, making them among the most compact stellar systems ever observed. At the same time, other galaxies at similar redshifts span several thousand light-years, rivaling the sizes of much later galaxies, despite forming when the universe was less than 500 million years old. This wide spread in sizes contradicts the expectation that early galaxies should follow a relatively tight size-mass relation. Ultra-compact galaxies are particularly puzzling. In several JWST fields, galaxies with masses comparable to the Small Magellanic Cloud appear compressed into volumes hundreds of times smaller. The implied stellar densities exceed those of modern elliptical galaxy cores and approach the densities seen in globular clusters, but on vastly larger mass scales. For example, a galaxy identified in the JWST survey at redshift 10.6 has an effective radius of approximately 300 light-years while containing over 2 billion solar masses in stars. Such densities raise immediate questions about how stars could form so tightly packed without rapid disruption from feedback or dynamical heating. Standard models tie galaxy size to the angular momentum of infalling gas, which in turn depends on the spin of the dark matter halo. At early times, halos are expected to have lower angular momentum, leading to smaller galaxies. However, the extreme compactness observed in some systems implies either that angular momentum was efficiently removed from the gas, or that star formation proceeded before the gas could settle into a larger configuration. Neither scenario is easily reproduced in simulations without introducing additional, often ad hoc, mechanisms. Equally problematic are the galaxies that appear too large. JWST has identified systems at redshifts 9-11 with half-light radii exceeding 2,000 light-years, sizes that models predict should not be reached until much later. These galaxies often show extended, diffuse stellar distributions rather than the tightly bound cores expected at such early epochs. Their existence suggests that some galaxies acquired significant angular momentum and spatial extent extremely quickly, despite the limited time available since the Big Bang. The presence of large early galaxies is difficult to reconcile with the rate of cosmic expansion. At redshifts above 10, the universe was expanding rapidly, and structures were only beginning to decouple from this expansion. Growing a galaxy to several thousand light-years across requires not only mass, but also time for stars to migrate outward or form in extended disks. Observational evidence, however, suggests that these large galaxies formed stars across their entire extent early on, rather than expanding gradually from compact cores. Kinematic data add another layer to the mystery. In both compact and extended early galaxies, gas and stars often show ordered motion rather than random dispersion. In compact systems, velocity dispersions are high, but not chaotic, indicating that the galaxies are gravitationally bound and dynamically mature. In larger systems, rotation curves extend across kiloparsec scales, suggesting that these galaxies had already established stable structures. This level of dynamical organization is unexpected given their extreme sizes, whether small or large. The coexistence of ultra-compact and extended galaxies at similar epochs points to divergent evolutionary paths operating almost simultaneously. Some galaxies appear to have undergone rapid dissipative collapse, concentrating mass into small volumes. Others seem to have experienced efficient angular momentum acquisition, allowing them to spread out quickly. The fact that both outcomes occurred within the same cosmic time frame challenges the idea that early galaxy evolution followed a single, predictable trajectory. Observations also indicate that size anomalies are not strongly correlated with the environment. Compact galaxies are found both in overdense regions and in relative isolation, as are the larger systems. This weak environmental dependence suggests that internal processes such as gas inflow geometry, star formation efficiency, and feedback coupling played a more significant role in determining size than external factors. It also complicates attempts to explain size evolution purely through mergers or environmental interactions. Comparisons with cosmological simulations highlight the severity of the discrepancy. While simulations can produce compact galaxies at high redshift, they typically do so at the expense of star formation or gas retention. Producing extended galaxies early on is even more difficult, often requiring unrealistically high halo spin parameters or suppressed feedback. No current simulation consistently reproduces the full observed range of galaxy sizes at redshifts above 8 while simultaneously matching their masses, star formation rates, and chemical properties. The implications extend beyond morphology. Galaxy size influences surface brightness, star formation intensity, and feedback efficiency. Ultra-compact galaxies concentrate star formation into small volumes, amplifying radiation fields and mechanical energy input. Yet many such systems show continued star formation rather than rapid quenching. Extended galaxies, on the other hand, spread star formation over large areas, which should reduce efficiency, yet they still achieve high total star formation rates. These conflicting behaviors challenge assumptions about how size regulates galaxy evolution. There are also consequences for interpreting observational surveys. Size affects detectability, especially at high redshift, where surface brightness dimming is severe. The discovery of both extremely small and unexpectedly large galaxies suggests that earlier surveys may have missed significant populations, biasing our understanding of early galaxy demographics. JWST's ability to detect low surface brightness features is now revealing structures that were previously invisible, further complicating comparisons with older datasets. Some researchers have proposed that early galaxies underwent rapid size evolution, expanding or contracting on short timescales. While dynamical processes such as gas inflows, starbursts, and feedback-driven outflows can alter galaxy sizes, the speed and magnitude required to explain the observations strain known physical limits. Expanding a galaxy by a factor of 5 within a few 100 million years, while maintaining coherence and continued star formation, remains difficult to justify theoretically. Observations have identified a growing number of early galaxies with sizes that deviate from predictions based on mass, environment, and redshift. These systems include both ultra-compact and extended galaxies at similar epochs, with a wide range of star formation rates and structural properties. The observed diversity provides empirical constraints on models of size evolution in the early universe. JWST observations at high redshift have identified galaxies with both unusually small and unexpectedly large physical sizes relative to their inferred ages and masses. These measurements indicate that galaxy size evolution during the first few 100 million years did not follow a uniform trend. The expanding observational sample provides data for testing models of how physical dimensions developed under early universe conditions, when galaxy collisions failed to leave scars. Given the extreme densities and rapid growth of early galaxies, collisions should have been common and devastating. In the standard picture of early cosmic evolution, galaxies formed in crowded environments where close encounters and mergers were frequent. These interactions were expected to leave unmistakable signatures: distorted shapes, tidal tails, asymmetric light profiles, multiple stellar nuclei, and chaotic internal motions. Yet JWST observations are revealing a growing number of early galaxies that appear remarkably smooth and undisturbed, even when other evidence suggests they must have experienced mergers. The absence of these expected scars presents a new and deeply puzzling contradiction. Deep imaging from JWST's NIRCam has uncovered galaxies at redshifts between 8 and 12, with clean morphologies and symmetric light distributions. These systems often show centrally concentrated stellar profiles or well-defined disks without the elongated tidal features typically associated with recent mergers. This is unexpected because, statistically, galaxies of such mass and age should have undergone at least one significant merger within their short lifetimes. In simulations, even minor mergers usually leave visible disturbances for hundreds of millions of years, yet many of these early galaxies appear dynamically settled. Kinematic data reinforce this mystery. Spectroscopic mapping using JWST's NIRSpec and ALMA shows smooth velocity gradients across several galaxies where mergers are otherwise implied by mass assembly requirements. Instead of abrupt velocity jumps or counter-rotating components, Gas and stars often exhibit coherent motion. In some cases, velocity dispersions are modest, suggesting that the systems are not dynamically heated as mergers should have caused. This level of kinematic order implies that either mergers were somehow unusually gentle or their effects dissipated far more rapidly than expected. Evidence for past interactions does exist in indirect forms. Stellar mass estimates indicate rapid growth that is difficult to explain through smooth accretion alone, implying that mergers likely contributed. Additionally, the number density of massive galaxies at high redshift suggests accelerated assembly that mergers would naturally facilitate. However, the visual and dynamical calm of these galaxies contradicts this inference. It is as if the mergers occurred without leaving behind the physical disruptions that normally accompany them. One possible explanation involves the nature of early galaxies themselves. Early systems were extremely gas-rich, with gas fractions often exceeding 70%. In such conditions, mergers between gas-dominated galaxies may behave differently from mergers between star-dominated systems. Gas can radiate energy efficiently and settle into new configurations more quickly than stars. If early mergers involve mostly gas, the resulting system could relax rapidly, erasing morphological scars on timescales much shorter than those seen in later epochs. While simulations do predict faster relaxation in gas-rich mergers, the degree of smoothness observed still exceeds expectations. The compactness of early galaxies may also play a role. When galaxies are small and dense, their dynamical timescales are short. Stars and gas can redistribute and settle more quickly after a disturbance. In ultra-compact systems, with effective radii of a few hundred light-years, relaxation times may be only tens of millions of years. This could allow merger signatures to fade rapidly, especially if the merger occurred early in the galaxy's history. However, this explanation requires that mergers happened extremely early, leaving little time for observation of disturbed phases. Another complicating factor is observational perspective. At extreme distances, subtle tidal features may fall below detection thresholds, even for JWST. Surface brightness dimming increases sharply with redshift, making faint structures difficult to observe. Nevertheless, simulations incorporating JWST's sensitivity suggest that major mergers should still produce detectable asymmetries and brightness fluctuations. The consistent smoothness observed across multiple surveys and instruments suggests that observational limitations alone cannot explain the absence of scars. Some galaxies show evidence of mergers in their stellar populations rather than their structure. Spectral analysis reveals composite stellar ages, indicating multiple episodes of star formation that could correspond to merger-driven bursts. Yet these age signatures are not accompanied by structural disturbances. This decoupling between stellar population history and morphology challenges the assumption that mergers necessarily disrupt galaxy structure in observable ways. It suggests that early galaxies may have absorbed mergers while maintaining or quickly re-establishing ordered configurations. The behavior of dark matter during early mergers may also differ from expectations. If dark matter halos were more centrally concentrated or interacted differently with baryonic matter under early conditions, mergers could produce less dramatic visible effects. Some theoretical work exploring self-interacting dark matter predicts smoother post-merger outcomes, though these models remain controversial and constrained by other observations. Still, the idea that dark matter physics could influence the visibility of merger scars adds another layer of uncertainty. The absence of scars also complicates the interpretation of galaxy demographics. If mergers are not easily identifiable through morphology at high redshift, then estimates of merger rates based on disturbed structures may be severely underestimated. This would affect our understanding of how galaxies assembled their mass and how frequently interactions occurred. It raises the possibility that the early universe was even more dynamically active than observed, but that its galaxies were unusually resilient to disruption. Comparisons with later cosmic epochs highlight how unusual this behavior is. In the nearby universe, even minor mergers often leave visible imprints, such as shells, streams, or warped disks, that persist for billions of years. The contrast with early galaxies, which appear pristine despite rapid growth, suggests that the physical conditions governing mergers were fundamentally different. Higher gas fractions, denser environments, and faster cooling may have allowed early galaxies to absorb impacts without lasting damage. The implications extend to theories of disk survival. In later epochs, mergers are thought to destroy disks, transforming galaxies into spheroidal systems. Yet early disk galaxies appear to have survived, or perhaps formed after merger events. This raises the possibility that disks in the early universe were either more robust or more easily reformed. Observations of smooth, rotating disks at redshifts above 10 support the idea that disk structures could emerge quickly even after significant interactions. Some researchers have proposed that early mergers were more aligned, occurring along filaments of the cosmic web. Such aligned mergers could preserve angular momentum and produce less disruption than random collisions. If galaxies merged along preferred directions, the resulting systems might retain coherent rotation and symmetric structures. While this idea is supported by some simulations, it remains uncertain whether alignment alone can account for the widespread lack of merger scars. Observations indicate that many early galaxy mergers did not produce visible structural disturbances. Despite mass growth implying past interactions, these systems often retain smooth morphologies and coherent kinematics. Data suggest that mergers in gas-rich, dense early galaxies may have redistributed mass and gas without producing lasting visible disruptions. JWST observations continue to identify early galaxies with smooth morphologies and coherent kinematics despite mass growth suggesting past mergers. These data indicate that morphological indicators alone may not reliably identify merger histories at high redshift. Measurements of internal motions reveal ordered kinematics in many early systems, providing constraints for models of galaxy assembly under primordial conditions. The unexpected order in galactic rotation. Following the surprising smoothness of early galaxies, despite likely mergers, astronomers turn their attention to the internal motions of stars and gas, expecting turbulence, chaotic flows, and irregular velocity fields. The early universe, after all, was a turbulent place, with high gas accretion rates, frequent interactions, intense feedback from supernovae, and energetic radiation from massive stars. Yet observations from JWST and ALMA are revealing a strikingly different picture. Many early galaxies exhibit surprisingly ordered rotation, with coherent velocity gradients resembling the well-structured disks of much later galaxies. This unexpected order in galactic rotation is one of the most puzzling aspects of early cosmic evolution. Integral field spectroscopy has been essential in uncovering these patterns. Using near-spec on JWST, astronomers have mapped emission lines such as OIIE 5007O and H-alpha in galaxies at redshifts between 7 and 10. The resulting velocity maps reveal smooth rotational profiles extending across several kiloparsecs. In some cases, rotation speeds reach 100 to 200 kilometers per second, comparable to the Milky Way today, despite the universe being only a few 100 million years old. These velocities are coherent rather than chaotic, indicating that angular momentum has been preserved or rapidly established during a period when theoretical models suggest turbulence should dominate. ALMA observations of cold molecular gas provide a complementary perspective. In several galaxies, carbon monoxide emission traces well-ordered rotation across extended disks. For example, GNZ11, a galaxy at redshift 10.6, exhibits a velocity gradient of roughly 120 km per second across a 1.5 kiloparsec disk. This corresponds to a rotation period of only 8 million years, a remarkably short timescale given the galaxy's age and the presumed chaotic environment. These findings suggest that even in the densest early systems, angular momentum was efficiently channeled into rotationally supported structures. The discovery of ordered rotation challenges existing models of angular momentum acquisition. Standard cosmological theory assumes that baryonic matter inherits angular momentum from dark matter halos, and that early mergers, inflows, and feedback processes largely disrupt this momentum. Yet the observed galaxies appear to have either preserved or rapidly re-established rotation. Some simulations suggest that cold gas streams along cosmic filaments could supply angular momentum efficiently, but reproducing both the amplitude and coherence of observed rotation has proven difficult. The data imply that early galaxies may have acquired angular momentum faster and more systematically than models predict. Ordered rotation also has implications for star formation. Rotational support reduces the effective pressure in the disk, allowing gas to collapse and form stars more efficiently in specific regions. In some observed galaxies, star formation is concentrated along rotationally supported disks rather than being widely scattered. Surface densities in these star-forming regions are high, often exceeding 1,000 solar masses per square parsec, which would normally lead to rapid feedback-driven turbulence. Yet the rotational order remains, suggesting that star formation in early galaxies proceeded in a remarkably coordinated fashion. The alignment of gas and stellar rotation adds another layer of intrigue. In many galaxies, stars and cold gas rotate along the same axis, with little evidence of misalignment. This implies a high degree of coherence between the processes that built the stellar component and those governing gas accretion. Achieving such alignment so early requires either a preferential direction for gas inflow from the cosmic web or mechanisms that realign stars and gas on surprisingly short timescales. Both scenarios challenge standard expectations, as misalignment is common in later epochs where mergers and interactions dominate. The smooth rotation is also surprising given the role of feedback. Supernova explosions, radiation pressure, and stellar winds were expected to stir the interstellar medium, generating turbulence that would disrupt coherent motion. Yet, observations indicate that even galaxies with extreme star formation rates of 50 to 200 solar masses per year maintain organized rotation. This suggests either that feedback couples inefficiently to the bulk of the gas in these dense systems, or that dense gas can dissipate energy quickly, allowing rotation to persist despite energetic events. Both possibilities highlight the remarkable resilience of early galaxies. Compactness may again play a role. Galaxies with high central densities have shorter dynamical times, allowing disturbed gas to settle into rotation rapidly. In ultra-compact systems, turbulent energy can dissipate in a few tens of millions of years, consistent with the observed coherence of rotation even after periods of intense star formation or minor mergers. However, this mechanism alone cannot explain the larger galaxies with extended disks that also display ordered motion. These systems require additional processes to maintain stability. Comparing observed rotation curves with theoretical expectations further emphasizes the anomaly. In the LCDM framework, galaxies at high redshift should exhibit rising rotation curves dominated by dark matter, with visible baryons contributing modestly. Instead, many early galaxies show flat or even slightly declining rotation curves within their inner regions, implying that baryonic matter is already dynamically dominant at scales of 1 to 2 kiloparsecs. This suggests that mass assembly in the inner regions was more efficient and centrally concentrated than models predict. The presence of coherent rotation across diverse galaxy sizes and environments hints at a broader principle. Early galaxies may have been able to self-organize efficiently despite the chaotic conditions of the young universe. Whether through aligned accretion streams, rapid gas cooling, or feedback regulation, angular momentum appears to have been preserved or restored in ways not captured by current simulations. This discovery forces a re-evaluation of how rotational support emerges in the first few 100 million years. The ordered rotation also intersects with other anomalies. Galaxies that maintain cold gas, survive mergers without scars, and display early chemical enrichment are often the same systems exhibiting smooth rotation. Together, these characteristics suggest that early galaxies were not only efficient at assembling mass, but also remarkably coordinated in their internal dynamics. The combination of high star formation rates, abundant gas, and stable rotation defies the expectations of turbulence-driven models. Future JWST observations will continue to expand the sample of rotating early galaxies and probe their internal dynamics at even higher redshifts. Measuring the prevalence, alignment, and rotational velocities of these systems will help clarify how widespread this order truly is. Already, the emerging picture is clear. Galaxies in the early universe were not chaotic blobs thrown together by chance, but highly organized systems capable of establishing rotational stability under extreme conditions. Observations show that early galaxies exhibit ordered rotation despite potential mergers, feedback, or turbulence. Velocity maps and kinematic data indicate that angular momentum in these systems was preserved, efficiently channeled, or rapidly re-established. These galaxies often also display smooth morphologies, persistent cold gas, and accelerated mass assembly, providing measurable constraints for models of early galaxy dynamics and evolution, ancient galaxies that stopped making stars too soon. While many early galaxies display rapid formation, smooth rotation, and chemical enrichment, a subset exhibits early cessation of star formation. These quenched galaxies, observed at redshifts between 3 and 7, contain mature stellar populations with little or no ongoing star formation, despite the universe being less than 2 billion years old. Observations indicate that these systems stopped forming stars far earlier than expected from standard models, in which massive star formation continues for hundreds of millions of years after gas accretion. Spectroscopic observations have been crucial in identifying these quenched galaxies. Using instruments such as JWST's NIRSpec, astronomers measure absorption features from evolved stars, revealing stellar ages exceeding 500 million years at redshift 6, implying that these galaxies formed the bulk of their stars when the universe was less than 300 million years old. In some cases, populations include a significant fraction of stars older than the inferred age of the cosmic reionization era, suggesting extremely early and intense bursts of star formation. One example, detected in the CEER's survey, shows an estimated stellar mass of over 10 billion solar masses, concentrated in a population that appears to have ceased forming stars by redshift 7. Photometric data further reinforce the quenching signal. These galaxies exhibit extremely red rest frame colours, consistent with aging stellar populations and minimal ongoing star formation. Infrared observations from JWST reveal little emission from heated dust or nebula lines, both indicators of active star-forming regions. ALMA follow-ups often detect minimal cold molecular gas, implying that the raw fuel for star formation has been exhausted or expelled. Some systems, despite their compact sizes, display stellar densities rivaling those of the densest modern ellipticals, underscoring the intensity of their early formation episodes. The rapid cessation of star formation in these galaxies is difficult to reconcile with conventional models of galaxy evolution. In the standard LCDM framework, massive galaxies are expected to continue forming stars as long as cold gas is available. Gas accretion from the intergalactic medium and minor mergers should supply fresh material, especially at high redshifts when the cosmic web is dense and inflows are efficient. That these galaxies shut down early suggests that additional processes must have intervened to prevent continued star formation. Several mechanisms have been proposed. One possibility is feedback from supermassive black holes. Active galactic nuclei can inject enormous energy into surrounding gas, heating it or driving it out of the galaxy entirely. Observationally, some early quenched galaxies coincide with evidence of AGN activity, though in many cases the inferred black hole mass is modest, raising questions about whether AGN alone can account for the rapid quenching supernova-driven winds are another candidate. Bursts of star formation can generate intense supernova explosions, expelling gas and halting further star formation. However, simulations suggest that in high-mass dense systems, gas can often survive or rapidly reaccrete, making complete quenching unlikely without additional mechanisms. Environmental factors may also play a role. Some quenched galaxies are found in dense protocluster regions where interactions, tidal forces, or ram pressure stripping could remove gas and suppress star formation. Yet, a substantial fraction of these galaxies exist in relative isolation, implying that quenching can occur independent of external environmental effects. This indicates that internal mechanisms, feedback, rapid gas consumption, or dynamical stabilization likely dominate. Chemical composition adds another layer to the puzzle. Spectroscopic studies reveal that early quenched galaxies are already enriched in heavy elements such as oxygen, carbon, and nitrogen. This indicates that multiple generations of stars formed and evolved within a few 100 million years, producing metals before star formation ceased. The high metallicity also enhances radiative cooling, which should facilitate further star formation, yet these systems remain dormant, suggesting that some suppressive mechanism overpowered the natural tendency of gas to cool and collapse. Stellar population modelling provides further constraints. Many early quenched galaxies show evidence of compact, centrally concentrated stellar distributions, implying that the initial star formation episodes were extremely efficient. Star formation rates during these bursts may have exceeded 500 solar masses per year in systems that are only a few 100 million years old. The combination of rapid consumption of gas and strong feedback could explain why subsequent star formation was suppressed, but achieving this degree of efficiency and timing requires fine-tuned conditions, rarely replicated in simulations. Observations also indicate that the quenching process is heterogeneous. Some galaxies cease star formation abruptly, while others show evidence of a more gradual decline over tens of millions of years. The diversity suggests that multiple pathways to quenching exist. In some cases, central black hole growth may dominate, while in others, stellar feedback or dynamical heating could play a leading role. Understanding the balance between these mechanisms is critical to explaining why early galaxies can stop forming stars long before standard models predict. The existence of early quenched galaxies also raises questions about subsequent evolution. Once star formation ceases, these systems evolve passively, with stellar populations aging and luminosities fading over time. If they remain undisturbed, they can become the progenitors of massive elliptical galaxies observed at lower redshifts. Some quenched galaxies at redshift 6 may already resemble the compact quiescent galaxies found at redshift 2, suggesting that the seeds of modern massive galaxies were in place remarkably early. Quenching at high redshift also challenges theoretical models that link star formation to halo mass. Many early quenched galaxies have halo masses of only 11 to 10, 12 solar masses, smaller than the thresholds typically associated with efficient feedback-driven suppression in simulations. The fact that these relatively modest halos can produce massive, quenched, stellar systems suggests that early star formation proceeded with extreme efficiency, generating both high stellar densities and rapid quenching in a fraction of a billion years. Observations of early quenched galaxies indicate that some systems built up large stellar masses and stopped forming stars within a few 100 million years. The specific mechanisms behind this rapid cessation remain under investigation, but likely involve a combination of gas physics, feedback processes, and dynamical effects that current simulations only partially reproduce. JWST observations continue to identify quenched galaxies at redshifts above 6. Some of these galaxies formed the bulk of their stellar mass, rapidly consumed their gas, and became dormant much earlier than standard models predict. These systems provide data for studying the mechanisms and timescales of early star formation shutdown, and offer constraints for refining models of early galaxy evolution, the missing feedback that should have destroyed them. If early galaxies exhibited rapid formation and sudden quenching, they also displayed resilience. Conventional theory predicts that the very processes fueling their growth, intense star formation, supernova explosions, and black hole activity, should disrupt or destroy these systems. Observations indicate that many early galaxies survive extreme conditions that simulations suggest would be catastrophic, with little evidence for complete disruption. High star formation rates in early galaxies often reach 100 to 500 solar masses per year, sometimes concentrated within regions only a few hundred parsecs across. In local analogues, such extreme starbursts produce violent feedback. Winds, radiation pressure, and supernova explosions inject enormous amounts of energy into the surrounding interstellar medium. In theory, this energy should drive gas outflows capable of halting further star formation or even unbinding the galaxy entirely. Observationally, however, many high redshift galaxies maintain dense reservoirs of cold gas despite ongoing star formation. For example, ALMA has detected molecular gas masses of up to 10 solar masses in galaxies at redshifts above 7, demonstrating that gas depletion is neither immediate nor catastrophic. Supernova feedback presents another problem. Massive stars in early galaxies live only a few million years before exploding as supernovae, producing shock waves capable of heating and expelling interstellar gas. In dense early galaxies, hundreds to thousands of supernovae could occur almost simultaneously, suggesting that their combined energy should disrupt the galaxy. Yet JWST and ALMA observations show many compact galaxies with high stellar densities remain intact, displaying neither widespread turbulence nor evidence of gas ejection on the scale predicted. Some simulations predict that star formation rates at these levels should lead to complete disruption within tens of millions of years, yet galaxies persist for hundreds of millions of years. Black hole feedback adds yet another layer of complexity. Early galaxies frequently host supermassive black holes, with masses approaching 10, 8 to 10, 9 solar masses, accreting gas at rates near the Eddington limit. Active galactic nuclei release prodigious energy, both as radiation and as powerful jets. In theory, this activity should clear central regions of gas, quench star formation, and potentially destabilize the host galaxy. Observational evidence, however, indicates that some of the most luminous early quasars reside in galaxies that are still actively forming stars at prodigious rates. The galaxy hosting quasar J, 313-1806, at redshift 7.64, contains over 1 billion solar masses in stars and shows both an active central black hole and substantial star-forming gas, suggesting that feedback has failed to halt growth. One explanation for this missing feedback is the density and compactness of early galaxies. Gas-rich, compact systems can absorb energy more efficiently, radiating it away before it has the chance to drive large-scale outflows. Simulations suggest that cooling times in dense, metal-enriched gas clouds can be extremely short, allowing gas to dissipate injected energy rapidly. This mechanism could explain why even the combined effects of supernovae and black hole activity fail to unbind the galaxy. Nevertheless, the observed resilience exceeds the levels predicted, implying that additional processes may be at work. The geometry of gas inflow may also mitigate feedback effects. Many early galaxies are fed by cold gas streams along cosmic filaments, which can continuously replenish material even as feedback attempts to expel it. This steady supply may allow galaxies to maintain star formation despite intense internal energy release. Observational evidence from kinematic mapping supports this idea, showing coherent inflows of gas along preferred axes in some high redshift systems. Such directed accretion may shield central regions from the full brunt of feedback, allowing galaxies to survive and grow despite the theoretical expectation of destruction. Magnetic fields could also contribute to early resilience. While poorly constrained at high redshift, magnetic fields may help channel supernova-driven energy away from dense regions or stabilize gas clouds against collapse. If magnetic tension suppresses turbulence or supports gas against gravitational collapse, feedback would be less effective at disrupting the overall structure. Observations of polarized emission in local starburst galaxies hint that magnetically mediated regulation can be significant, though its role in the early universe remains speculative. The failure of feedback to destroy early galaxies is evident across multiple independent measures. Velocity dispersion measurements show that many massive systems maintain low internal turbulence despite extreme star formation. Cold gas reservoirs remain abundant, with ALMA detecting molecular line emissions even in the most active galaxies. Stellar density profiles indicate that the bulk of stars are centrally concentrated, unaffected by feedback-driven mass loss. Together, these observations suggest that the physics of early galaxies allowed them to resist the very processes expected to limit their growth. Interestingly, the missing feedback is closely linked to other anomalies. Galaxies that survive intense star formation often also exhibit smooth morphologies, coherent rotation, and early chemical enrichment. These characteristics imply that early galaxies were remarkably coordinated systems, capable of maintaining structural integrity while processing vast amounts of gas and forming stars at extreme rates. The same conditions that allow mergers to leave no visible scars and rotation to remain organized may also explain why feedback fails to disrupt these galaxies. Some researchers have proposed that feedback may be delayed rather than absent. In this scenario, energy from supernovae and black holes primarily affects lower density gas in the outskirts, while the dense central regions remain largely untouched. Observations of high redshift galaxies with central star formation and extended gas halos support this idea, suggesting that feedback may preferentially impact the circumgalactic medium rather than the dense inner galaxy. If so, the observable effects of feedback could be subtle, hiding its destructive potential from direct detection. Observations show that in the early universe, compact galaxies with dense gas, filamentary accretion, and rapid cooling often persist despite intense energy release from star formation and black hole activity. Simulations incorporating known physics of feedback and accretion sometimes fail to reproduce the observed population of early galaxies, suggesting that additional processes or efficiencies may need to be considered. Observations indicate that early galaxies often withstand energy release from star formation and black hole activity without large-scale disruption. Many systems retain massive stellar components, dense gas reservoirs, and stable structural configurations during the first billion years, despite conditions that simulations suggest would lead to catastrophic feedback effects. When simulations and reality stopped agreeing, as the discoveries from JWST, ALMA, and other observatories accumulated, a clear pattern emerged. The most advanced cosmological simulations were failing to reproduce the properties of early galaxies. The mismatch spans multiple aspects of galaxy formation, including stellar mass, chemical enrichment, rotation, and star formation rates. Observations reveal differences between simulated outcomes and actual measurements of high redshift galaxies. State-of-the-art simulations, such as Illustris TNG, Eagle, and Fire 2, were designed to incorporate the full complexity of galaxy formation, dark matter halos, baryonic accretion, star formation, supernova and AGN feedback, radiative transfer, and cosmic expansion. These simulations successfully reproduced many properties of galaxies at redshifts below 3, including stellar mass functions, galaxy sizes, and large-scale structure. However, when extrapolated to redshifts above 7, they systematically underpredict the abundance of massive galaxies. Observational surveys now report galaxies with stellar masses of 10 to 10, 11 solar masses at redshifts, 9 to 12. But simulations often produce fewer than 10% of such systems in equivalent cosmological volumes. The problem extends to star formation rates. Many simulated galaxies at Z is greater than 8 struggle to exceed 50 solar masses per year, while observations indicate multiple systems forming stars at 200 to 500 solar masses per year. GNZ11, one of the most distant confirmed galaxies at redshift 10.6, shows star formation around 50 solar masses per year, already stretching the upper limits of some models. And more extreme cases are emerging from JWST deep field data. The discrepancy suggests that simulations are either missing key physical processes or underestimating the efficiency of early star formation. Another glaring conflict involves galaxy morphology. Simulations predict that high redshift galaxies should be highly irregular, dominated by mergers, and prone to fragmentation. Turbulent flows, gravitational instabilities, and chaotic gas inflows are expected to prevent the formation of smooth disks or coherent rotational structures. Yet JWST and ALMA reveal numerous examples of well-ordered disks and spiral-like features at redshifts above 7, with rotation velocities of 100-200 km per second and low velocity dispersion. The emergence of such rotational order in simulations requires fine-tuning that has yet to be physically justified. Chemical enrichment also exposes major discrepancies. Many early galaxies show substantial oxygen, carbon, and nitrogen abundances, implying several generations of massive stars had already formed and evolved. Standard simulations struggle to reproduce this level of enrichment so early, as they assume star formation proceeds gradually and feedback regulates metal distribution. Observed high redshift galaxies indicate that metals were produced and retained efficiently, challenging models that predict widespread ejection or slow recycling. For example, measurements in a galaxy at Z equals 9 indicate an oxygen abundance of roughly 0.2 solar, yet simulations predict less than 0.05 solar at the same epoch. The missing feedback problem compounds these inconsistencies. Simulations rely on supernova and AGN feedback to regulate star formation and prevent overproduction of massive galaxies. Yet observations show that early galaxies can simultaneously harbour active supermassive black holes, form stars at extreme rates, and retain cold gas without catastrophic disruption. The inability of simulated feedback to reproduce this resilience highlights a fundamental mismatch between the modelled physics and the complex, multi-scale processes occurring in the real early universe. Attempts to reconcile simulations with observations by adjusting parameters have met limited success. Increasing star formation efficiency can produce more massive galaxies, but this often results in overproducing stellar masses at lower redshifts. Modifying feedback prescriptions can prevent runaway star formation, but often destroys the very disks and structures that are observed. Adding more detailed chemical evolution or enhanced gas accretion improves agreement for some properties, but no single adjustment simultaneously reproduces mass, rotation, metallicity, and compactness. The failures suggest that simulations are missing a fundamental ingredient in the physics of early galaxy assembly. The discrepancy also extends to environmental effects. Simulations predict that the densest protocluster regions should accelerate galaxy formation, yet JWST is finding massive, mature galaxies in relatively underdense regions. These observations imply that rapid mass assembly can occur even without the dense cosmic web structures assumed to drive accelerated growth in models. Filamentary cold flows, traditionally incorporated in simulations, may need to be re-evaluated in terms of efficiency, orientation, and angular momentum transport to account for these unexpected outcomes. Angular momentum is another area where simulations falter. Early disks in models are often highly turbulent and kinematically unstable, yet observed high redshift galaxies display coherent rotation, smooth velocity gradients, and alignment between stars and gas. Producing such ordered structures in simulations requires precise initial conditions and assumptions about gas inflow, cooling, and merger history, suggesting that current models may oversimplify or misrepresent the processes that preserve angular momentum in dense, early environments. The gap between simulated and observed galaxy populations has broader implications. Cosmological models rely on simulations to connect dark matter structure formation with baryonic processes. If the models cannot reproduce the abundance, structure, and chemical properties of early galaxies, this calls into question assumptions about halo occupation, gas cooling, and star formation efficiency in the first billion years. It also raises the possibility that unknown physics, perhaps related to dark matter behavior, early black hole seeding, or radiative cooling, may play a more prominent role than currently accounted for. Recent efforts to address these challenges include higher resolution simulations, enhanced feedback models, and alternative prescriptions for star formation in dense, compact systems. Projects like Blue Tides and Romulus C attempt to model extreme early environments with greater physical realism, but even these cutting-edge simulations only partially reproduce the observed properties. Discrepancies remain in galaxy number densities, rotation curves, chemical enrichment, and quenching patterns, reinforcing the idea that the early universe is far more extreme and efficient than current theory predicts. Observed early galaxies differ from simulated predictions in several ways. Models forecast gradual, chaotic growth moderated by strong feedback, while data show rapid mass assembly, coherent rotation, high metallicity, and stable structures in galaxies at Z is greater than 7. These discrepancies indicate that current simulations do not fully reproduce the physical processes that shaped galaxies during the first billion years. The divergence between simulations and observations has emphasized the need for direct data from JWST, ALMA, and other observatories. New measurements provide empirical constraints that simulations must account for, revealing differences between predicted and observed properties of early galaxies. Observations continue to identify early galaxies that differ from simulated expectations. Beyond rapid formation, ordered rotation, and early quenching, new systems are being found that present additional discrepancies between models and data, highlighting areas where simulations require further refinement to reproduce the observed diversity and properties of high redshift galaxies. By the time JWST and ALMA began delivering their unprecedented views of the early universe, astronomers expected to find a handful of exceptional systems challenging the theory. Surveys now report dozens of massive, luminous, chemically enriched, and dynamically mature galaxies at redshifts between 7 and 15. These observations indicate that such galaxies were present in measurable numbers, showing higher efficiency in star formation and chemical enrichment than some early models predicted. One striking example is Goodluck's Z13, identified in the CEER's deep field at a redshift of 13.2. Its stellar mass is estimated at over 8 billion solar masses, with star formation rates exceeding 200 solar masses per year during its peak. ALMA observations detect substantial dust emission, indicating a mature interstellar medium enriched with metals in less than 350 million years after the Big Bang. JWST imaging reveals a smooth, elongated morphology, consistent with a rotating disk rather than the chaotic mergers simulations predicted at this epoch. Its existence alone challenges conventional timelines, requiring both rapid gas accretion and extreme star formation efficiency. Another notable case is SPT 031158, a system at redshift 6.9, which contains two massive galaxies separated by only 30 kiloparsecs, yet shows remarkably smooth stellar distributions. ALMA observations reveal over 10 solar masses of molecular gas, much higher than predicted by LCDM models for galaxies of this size and epoch. The system also shows surprisingly high metallicity, with oxygen abundances roughly 1/5 that of the Sun, suggesting multiple generations of star formation had already occurred. Its dynamics indicate well-ordered rotation in both components, defying expectations of turbulence from mergers. Even more extreme are candidates identified at redshifts above 14, such as CEER's 93316 and GLASS Z15, which appear to contain stellar masses of 10, 8 to 10, 9 solar masses, when the universe was only 250 to 300 million years old. The inferred luminosities of these systems exceed predictions from standard models, suggesting they are forming stars at rates near 5,100 solar masses per year, despite the limited time available for gas accretion and cooling. These galaxies demonstrate that the earliest stages of cosmic evolution were capable of producing fully formed, star-rich systems in periods previously thought impossible. Dust and metal enrichment in these galaxies further complicate the picture. Observations of far-infrared emission lines from ALMA indicate significant oxygen, carbon, and nitrogen abundances, requiring multiple generations of stars to have already lived and died. The presence of dust in such young galaxies also implies that supernovae rapidly processed and expelled metals into the interstellar medium. This contradicts earlier assumptions that metal production would lag behind star formation, highlighting a level of chemical evolution efficiency previously unseen. Rotation and structural order remain another area where rule-breaking galaxies defy expectations. Many of the newly discovered high redshift galaxies exhibit coherent rotation curves, often aligned between stellar and gaseous components. Velocity dispersions are surprisingly low, in some cases below 70 kilometers per second, implying that angular momentum stabilization occurred far earlier than simulations suggest. JWST's NIRCam imaging shows disk-like profiles, central bulges, and even hints of spiral structure in galaxies at redshifts above 10, challenging the long-held assumption that early galaxies should be dominated by chaotic mergers. Supermassive black holes further complicate the anomaly list. Quasars, such as J1000, 342 plus 0928 at redshift 7.54, host black holes exceeding 7.8 times 10, 8 solar masses. These central engines coexist with massive star-forming galaxies, indicating that black hole growth and stellar mass assembly can proceed in parallel without immediately quenching star formation. This scenario contradicts models in which AGN feedback efficiently regulates or halts star formation, reinforcing the emerging theme that early galaxies were far more robust and self-regulated than predicted. The environment of these galaxies adds another twist. Some are located in dense proto-cluster regions, while others exist in apparent isolation, suggesting that extreme early growth does not require crowded cosmic neighborhoods. This observation challenges assumptions that only high-density regions can accelerate galaxy formation. Filamentary inflows and cold gas accretion may allow rapid growth even in underdense regions, a scenario only partially captured by current simulations. Surveys like Cosmos Webb, JADES, and GLASS report dozens of high redshift galaxies whose masses, luminosities, and morphologies exceed theoretical predictions. The cumulative number of these systems is growing, and their properties are consistent across multiple independent observations. This indicates that galaxies with unexpectedly high mass and structural maturity were present in measurable numbers during the early universe. These observations provide data relevant to the reionization history of the universe. The high luminosities and star formation rates of these galaxies suggest that early galaxies contributed significantly to the ionizing photon budget. The presence of numerous mature, bright systems at redshifts 10-15 provides new empirical constraints on the timing and sources of cosmic reionization. As the catalogue of these rule-breaking galaxies grows, so too does the challenge for theoretical astrophysics. Each new discovery pushes the boundaries of what is considered physically plausible, demanding adjustments to models of star formation efficiency, gas accretion, feedback, chemical evolution, and angular momentum transport. The emerging consensus is that early galaxy formation was both rapid and efficient, producing massive, chemically mature, and dynamically ordered systems in epochs where conventional physics would predict only small, primitive protogalaxies. The growing list of anomalous galaxies represents not isolated curiosities, but a systematic challenge to existing cosmological models. Systems such as Good Luck Z13, SPT 031158, CEARS 93316, and numerous others highlight the diversity and maturity of early galaxies, revealing a universe far more complex, productive, and organized than previously imagined. As JWST continues to probe deeper and ALMA traces the cold gas and chemical composition of these systems, the number of rule-breaking galaxies is likely to expand, making it increasingly clear that our understanding of cosmic dawn is incomplete, and that the early universe was a far more dynamic and extraordinary place than ever predicted.